In mathematics, an embedding is one instance of some mathematical structure contained within another instance, such as a group that is a subgroup. When some object X is said to be embedded in another object Y, the embedding is given by some injective and structure-preserving map F. X, Y. The precise meaning of structure-preserving depends on the kind of mathematical structure of which X and Y are instances. In the terminology of category theory, a structure-preserving map is called a morphism. The fact that a map F X, Y is an embedding is often indicated by the use of a hooked arrow. Thus, on the other hand, this notation is sometimes reserved for inclusion maps. Given X and Y, several different embeddings of X in Y may be possible. In many cases of interest there is a standard embedding, like those of the natural numbers in the integers in the rational numbers, the rational numbers in the real numbers, and the real numbers in the complex numbers. In such cases it is common to identify the domain X with its image F contained in Y, so that X, Y. Topology and geometry. General topology. In general topology, an embedding is a homeomorphism onto its image. More explicitly, an injective continuous map between topological spaces and is a topological embedding if yields a homeomorphism between in. Intuitively then, the embedding lets us treat as a subspecific. Every embedding is injective and continuous. Every map that is injective, continuous and either open or closed is an embedding. However, there are also embeddings which are neither open nor closed. The latter happens if the image is neither an open set nor a closed set in. For a given space, the existence of an embedding is a topological invariant. This allows two spaces to be distinguished if one is able to be embedded in S space while the other is not. Differential topology. In differential topology, let M be smooth manifolds and be a smooth map, then is called an immersion if its derivative is everywhere injective. An embedding, or a smooth embedding, is defined to be an injective immersion which is an embedding in the topological sense mentioned above. In other words, an embedding is diffeomorphic to its image, and in particular the image of an embedding must be a submanifold. An immersion is a local embedding when the domain manifold is compact. The notion of a smooth embedding is equivalent to that of an injective immersion. An important case is, the interest here is in how large must be for an embedding, in terms of the dimension of. The Whitney embedding theorem states that is enough, and is the best possible linear bound. For example, the real projective space RPM of dimension, whereas a power of 2, requires for an embedding. However, this does not apply to immersions. For instance, RP2 can be immersed in as is explicitly shown by Boy's surface, which has self-intersections. The Roman surface fails to be an immersion as it contains cross-caps. An embedding is proper if it behaves well. W, R, T. Boundaries. One requires the map to be such that, and, is transverse to in any point if. The first condition is equivalent to having in. The second condition, roughly speaking, says that F is not tangent to the boundary of Y. Riemannian geometry. In Riemannian geometry, let N be Riemannian manifolds. An isometric embedding is a smooth embedding F. Mn which preserves the metric in the sense that G is equal to the pullback of H by F, i.e., G equals F asterisk H. Explicitly, for any two tangent vectors we have analogously. Isometric immersion is an immersion between Riemannian manifolds which preserves the Riemannian metrics. Equivalently, an isometric embedding is a smooth embedding which preserves length of curves. Algebra. In general, for an algebraic category C, an embedding between two C algebraic structures X and Y is a C-morphism E, XY which is injective. Field theory. In field theory, an embedding of a field E in a field F is a ring homomorphism sigma, EF. The kernel of sigma is an ideal of E which cannot be the whole field E, because of the condition sigma equals 1. Furthermore, it is a well-known property of fields that their only ideals are the zero ideal and the whole field itself. Therefore, the kernel is 0, so any embedding of fields is a monomorphism. Hence, E is isomorphic to the subfield sigma of F. This justifies the name embedding for an arbitrary homomorphism of fields. Universal algebra and model theory. If sigma is a signature in a sigma structures, then a map is a sigma embedding IFF. All the following holds. Is injective. For every ARY function symbol and we have. For every ARY relation symbol and we have IFF. Here is a model theoretical notation equivalent to. In model theory there is also a stronger notion of elementary embedding, order theory and domain theory. In order theory, an embedding of partial orders is a function f from x to y such that, in domain theory, an additional requirement is directed. Metric spaces. A mapping of metric spaces is called an embedding if for some constant. Normed spaces. An important special case is that of normed spaces. In this case it is natural to consider linear embeddings. One of the basic questions that can be asked about a finite-dimensional normed space is, what is the maximal dimension such that the Hilbert space can be linearly embedded into with constant distortion? The answer is given by Dvoretsky's theorem. Category theory. In category theory, there is no satisfactory and generally accepted definition of embeddings that is applicable in all categories. One would expect that all isomorphisms and all compositions of embeddings are embeddings, and that all embeddings are monomorphisms. Other typical requirements are, any extremal monomorphism is an embedding and embeddings are stable under pullbacks. Ideally the class of all embedded subobjects of a given object, up to isomorphism, should also be small, and thus an ordered set. In this case, the category is said to be well-powered with respect to the class of embeddings. This allows to define new local structures on the category. In a concrete category, an embedding is a morphism F, a B which is an injective function from the underlying set of A to the underlying set of B and is also an initial morphism in the following sense. If G is a function from the underlying set of an object C to the underlying set of A, and if its composition with F is a morphism FG, CB, then G itself is a morphism. A factorization system for a category also gives rise to a notion of embedding. If is a factorization system, then the morphisms in M may be regarded as the embeddings, especially when the category is well-powered with respect to M. Concrete theories often have a factorization system in which M consists of the embeddings in the previous sense. This is the case of the majority of the examples given in this article. As usual in category theory, there is a dual concept, known as quotient. All the preceding properties can be dualized. An embedding can also refer to an embedding functor.